charge. And now I go inside. And I slosh around inside. I feel no force anymore. There is no electric field inside. So as I move around inside, I experience no force. That means I do no work. So that means that the potential must remain constant. So the absence of an electric field here implies that the electric potential everywhere is exactly the same. Inside is the same as on the sphere, because no further work is needed in marching around with a test charge. And so for this special case, I could make a graph of the electric potential versus R, and this is then the radius of the Van de Graaff, and that will be a constant all the way up to this point, and then it would fall off as 1 over R here. And for the numbers that we have chosen, the potential at the maximum here would be 300,000 volts. Just as when you look at maps, where you see contours of equal height of mountains, which we call equal altitudes, here we have surfaces of equipotential. And if you had a point charge, or if you had the Van de Graaff, these surfaces would be concentric spheres. The further out you go, if the charge is positive, the lower the potential would be. They would be nicely spherical surfaces. Suppose now we had more than one charge. We had a plus Q1 charge, and we had a minus Q2 charge, for instance. And you're being asked now, what is the potential at point P? Well, now the electric potential at point P, Vp, is the potential that you would have measured if Q1 had been there alone. And you have to add the potential that you would have seen if Q2 had been there alone. Just adding work per unit charge for one with work per unit charge of the other. And if this is negative, then this quantity is negative, and this is positive. So when you have configurations of positive and negative charges, then of course, depending upon where you are in space, if you're close to the plus charge, the potential is almost certainly positive, because the 1 over R is huge. If you're very close to the negative charge, again, the 1 over R of this little charge will dominate, and so you get a negative potential. And so you have surfaces of positive potential, and you have equipotential surfaces of negative potentials, and so there are surfaces which have zero potential. And they're not always very easy to envision. But what I want to show you is some work that Maxwell himself did in figuring out these equipotentials. And so I have here a transparency of publication by Maxwell. You see a charge, let's assume it is plus 4 and plus 1, could be minus 4 and minus 1, but let's assume they're plus. And you see the green lines, which we've seen before, which are the field lines. Don't pay any attention to the green field lines now. The red lines are equipotentials, and you have to rotate them about the vertical because they are, of course, surfaces. This is three-dimensional. I have not drawn all the equipotential surfaces in red because they become too cluttered here. But I've tried to put most of them in red. Since this charge is positive and that charge is positive, everywhere in space, no matter where you are, the potential has to be positive. There is not a single point where it could be negative. If you are very far away from the plus 4 and the plus 1, then you expect that the equipotential surfaces are spheres, because it's almost as if you were looking at a plus 5 charge. So it doesn't surprise you that when you go far out, that you ultimately get spherical shapes. When you're very close to the plus 4, they are perfect spheres. When you're very close to the plus 1, they are perfect spheres. But then when you're sort of in between, neither close to the +4 nor to the +1, they have this very funny shape. It reminds me the shape of this balloon a little bit. Sort of like this. You see? And there is one surface which is most unusual, equipotential surface, which here has a point where the electric field is 0. Sort of like twisting the neck of a goose. You get something like this. And so you have here a surface which has a point here, and it is exactly at that point where the electric field is 0. That does not mean that the potential is 0. Of course not. The potential is positive here. If you come with a positive charge from the lobby 7 and you have to march up to that point, you have to do positive work. You have to overcome both the repelling force from the +4 and the repelling force from the +1. But finally, when you reach that point, you can rest, because there is no force on you at that point. That's what it means that the electric field is 0. It does not mean that you haven't done any work. So never confuse electric fields with potentials. I want to draw your attention to the fact that the green lines, the field lines, are everywhere perpendicular to the equipotentials. I will get back to that during my next lecture. That is not an accident. That is always the case. Now, Maxwell shows you something that is a little bit more complicated. Here, he calculated for us the equipotential surfaces. The red ones are the surfaces. Again, you have to rotate them about the vertical to make it three-dimensional. And now we have a -1 charge and a +4. And so whenever it is red, the surface, the potential is positive. And whenever I have drawn it blue, the potential is negative. First, if we were very far away from both the +4 and the -1, you expect to be looking at a charge which is effectively +3. And so if you go very far away, for sure, the potential is everywhere positive. And you expect them to be spherical again. If you look here, you're very far away from the +4 and the -1. Indeed, this has already the shape of a sphere. So that's clear, that the +4 and the -1 far away behave like a +3. If you're very close to the +4, you get nice spheres around the +4, positive potential. If you're very close to the -1, notice that the blue surfaces are almost nice spheres, but now they're all negative, because you're very close to the -1. So a negative potential. There is here one surface which now has 0 potential. It has to be,